So in this video, we're going to talk about casting in C++. Let's jump into main.cpp. Right now, we have a main function which does nothing but returning 0. And to save up some time, I have defined some user-defined data types. We're going to come back to these later. Let's just start to talk about C-style casting first, maybe. Let's say I have a int I, which is the value of 5. Then I have a double star D, and let's assign ampersand I. Let's assign the address of I into this. If I do that, Clang is throwing an error. Let's take a look at diagnostics. It says cannot initialize a variable of type double star to an R value of type int star. Okay, I can fool Clang. I can say I want to cast it to double star. By the way, this is C-style casting, so you have parentheses, and then in between you mention the type that you want to cast your object to. So my object is of type int star. Now I'm casting into double star, and it seems like Clang buys this, because we have fooled him. And this is so bizarre that even you can cast this thing into a particle star, and Clang basically is not going to complain at all. And you can compile this. So that is one of the many reasons that as a C++ programmer, you should never ever use C-style casting. So what is the alternative in C++? The alternative is using static casting, for example. You can do a static cast. Then you can provide the desired type in this angled brackets. By the way, this brings memories about templates, right? So let's take a look at this. Now if I take a look at diagnostics, it says a static cast from int star to double star is not allowed. So Clang is saying not on my watch. So if you're doing some stupidly stuff with your types, then at least you have the assistance of Clang or the compiler that you are having to help you basically, hey, you're doing something stupid most probably. But let's say you say, nah, I'm not doing something stupid. I really know what I'm doing. I really want to cast this int star to a double star because I know what I'm doing. In that case, let me comment this line. In that case, you can use something called as reinterpret cast. Reinterpret cast is another type of casting in C++, which is mostly used for low-level stuff. It is used to convert convert unrelated data types to each other, for example, into int star or int star to double star or things of that nature. So you see that when I use reinterpret cast, Clang is happy, is not throwing any errors because Clang is relying on me as the programmer that he knows that what he's doing. And by the way, when you're using reinterpret casting, if you want to access the original data, you can't do it. So in other words, I cannot, for example, come down here and say, hey, I want to dereference D, just like that. No, because I messed up with the types, right? So I have to cast it back to the original type. So in other words, I need to do another reinterpret casting. Excuse me. And then I cast it back to int star, and I feed the D right there. And of course, I forgot to add a end line here. And let's put a space right there. If I compile this and I run it, you see that I get the value of I, right? So this is, so far we've seen static casting and reinterpret casting. You see that we see the intention. So when you say static casting, we know the intention of the programmer, what it wants to do. When we see a reinterpret casting, we know the intention of the programmer, what it wants to do. It wants to do, for example, some unrelated data types conversion. Another things which catches my eye is that we are using these angled brackets with a type in between, which gives us the notion of templates, which probably also gives you the idea that is it possible to define our own sort of type conversions? Let's check this out. Here it comes with this user data types that I defined earlier. Let's say I inject a particle P1 and I assign a diameter of 3 millimeters. I want to inject another particle called P2, and this time, let's say I forgot to mention a diameter size. So Clang is complaining. Let's take a look at it. It says no matching constructor. Of course, it's because we got to go to particle and add a default constructor. I'm going to ask nicely from Clang to do that for me. Now you see that Clang is happy because we do have a default constructor right now. But we know that P2 is not a valid particle, right? Because D is a pointer. And if you don't provide a diameter, then it's going to be a null pointer. And at any point, if I try to dereference the null pointer, I'm going to get a segmentation fault. Who wants to figure that out, right? So let's say if down the line I want to do some sort of sanity checking. In other words, I want to be able to say if P2, then std cout P2 is not a valid particle. So right now, if I do that, you see that Clang is complaining. Take a look at diagnostics. It says value of type particle is not contextually convertible to Boolean. Let's try this with static casting. Maybe with a static casting. Last time we used a static casting, it worked. Let's try it here. We're going to cast it to a Boolean, and we're going to pass in the object of P2. If we do that, then Clang comes and says cannot convert particle to bool without a conversion operator. So when Clang is talking about conversion operator, it means that maybe there's a way that in our particle class we can define something like a conversion operator. We can define it by saying operator bool, this is the type that we want to have. And we do a sanity checking on D as our data member. If it's not a null pointer, it should return true, of course. And then we go down here, we say else. It should return false. So now if I come back down here, of course I have to put a negate right there because if it's a null pointer, it's going to return false, and this is not a valid particle, so this means in order to make this one true, you're going to negate it so that this line is getting executed. So if I compile this and I run it, it says P2 is not a valid particle, which correctly says it. So now you see that you can also define your own conversion types for your custom data types. What else do we have in casting? We have something called as const casting. And as you might have guessed, it's used for casting away the constness of objects that you're working. But you shouldn't misuse this thing. In other words, if an object is really a constant object, then an attempt to do this const casting and manipulate that thing is going to result into undefined behavior. So const casting, as an example, we can see it, for example, in our particle class. Let's say I want to define a member function right here, and it's going to be compute drag for my particle. Of course, in order to compute drag, I'm going to say compute drag. In order to be able to compute drag, I need to have access to the velocity field of the continuous field around the particle, right? So I'm going to pass a continuous phase reference as CP, continuous phase. And the first thing I want to do is to access to my velocity field, and that is with cp.velocity field, and then I had that access function up here, which gives me a const access to velocity field. Coming back to here, if you do that, you see that Clang is complaining. Let's take a look at it. It says this argument to member function velocity field has type const continuous phase, but the function is not marked as const. So to solve this issue, of course you can throw in a const here and then this issue is solved. But I want to show you how you can resolve this issue with const casting. In fact, this CP is not a const object. The only reason that we put a const reference here is to visually and vividly, clearly say that we are not going to mess up with this continuous phase object right there. And that's why we are sending this thing as a const reference. So here, I can use const casting. I can cast this thing to a continuous phase reference, and I'm going to pass in this CP object. And you see that Clang is super happy. So this is one use case of const casting. What else do we have? We have dynamic casting. So what is dynamic casting? Dynamic casting is pretty much tied down to the idea of polymorphism in C++ and class hierarchies. So right now I have a droplet right here, which is a sort of particle, a droplet, and it inherits publicly from particle, and it has exclusively a viscosity because it's a liquid, and it has a constructor which uses the particle constructor to give the diameter. So this means I can come down here and I can generate a droplet, let's say D1 with a diameter of 6 millimeters. I can assign a pointer to a particle as PDR. I can assign the ampersand, the address of D1. I can do that implicitly, and this is completely valid. You see that Clang is not complaining. And the reason is because droplet is a derived class of particle. But I, as a good programmer, maybe you want to clearly represent your intentions. You say static cast to a particle star. And then you want to also use parentheses around this thing. And now let's say down the line, I generate sort of a vector or a list of particle pointers, and then I pass it to a library to compute some stuff for me on my particles or on my droplets. And then that library gives me back my particle pointers. But I am not 100% sure whether is it really my droplets or is it really my particles. The way to check that is, let's check this thing. I generate a droplet star, a droplet pointer. I call it as dptr, a droplet pointer, and then I use dynamic cast. And of course the type should be droplet. Then I pass in the pointer here. If I do that, now I can do sanity checking again. I can say if, then dptr, then I'm going to say std cout, I'm really a droplet. Or else, I am a particle. So the way dynamic cast works is that you do runtime type inquiry, and this is tied to the concept of runtime RTTI in C++ or runtime type identification. So you're checking this pointer and you're assigning this to a droplets type pointer. So the way that dynamic cast works, if this thing points to an object which is actually a droplet, this pointer is going to be a valid pointer. If this pointer is not pointing to an object which is really a droplet, in other words, it's a particle, then this is going to be filled with null pointer. So here you can do your sanity checking, your type checking at runtime. By the way, when it's dynamic, it means that it happens at runtime, so you're going to have a slight overhead associated to that. And same way, when we are having static casting, it means that it happens at compile time, so there is no overhead, and type checking is done by the compiler at compile time. So here you see that you're saying that I'm really that droplet that you sent to that library, and now I'm back. If I compile this and I run it, you see that it says I'm really a droplet. So there we go. We have seen 4 different types of casting in C++ in a nutshell. And the general advice is that avoid using casting in general. because casting is sort of a nasty feature of C and C++ languages. But that was in an ideal world. But if you have to use some sort of casting, then never ever use C style casting as a C++ programmer. Use the provided alternatives with clear indications of your intentions when you are doing those type of castings. I hope you learned something from this video and hope to see you in the next one.